real exam questions. This is question 9, and it deals with slab design and yield lines. The question goes as follows. A square slab with a sign B can withstand a total load of Q0 kilonewton per square meter in the ultimate limit state persistence. For an air duct or something else, for an air duct, a square opening with side B/3 is made in the center of the slab. What is the maximum load capacity of the slab now? We start with the design load without the reservation, and we will compare this with the design load with the reservation. We have here the square slab. The edges of the slab are the axis of rotation, and when the two axes of rotation crosses, then the yield line starts. So in the four corners, the yield line starts, and we got this as the yield line pattern. The work done by the external forces must be equal to the work done by the internal forces. So we can write it in a simplified formula like this. We see that the work done for the external forces is equal to the surface of this triangle, which is B times B/2 divided by 2 and multiplied by the mean deflection of the triangle is delta/3. That's this portion of the formula, but we got it 1, 2, 3, 4 times. Please note that we could have obtained it much quicker because everything is comprised out of triangles. So we just take the total surface times the load and we divide it by 3 because the mean deflection is delta/3. On this side of the equation, this is the work done by the internal forces. So we take an axis of rotation and we project this bending moment on the axis of rotation. So it is m times B/2 and times the angle of rotation, which is delta divided by B/2. And this we will have on this side once, this 2, 3, 4, 5, 6, 7, and 8. So we'll have this 8 times this expression. When we now rearrange it for the bending moment, so the bending moment is Q0 B squared over 24. Consider Q the design load with the reservation. Then we got this is the reservation. Then again, you have the axis of rotation on all the sides, the 4 sides. The yield line starts in a corner like this, but stops at the edge of the slab. So these are the 4 yield lines. We calculate first the work done by the external forces. So this will be first we take the rectangular sections. So this for the rectangular section is B/3 times B/3 divided multiplied by the mean deflection. This is delta. This portion is the deflection of delta. So the mean deflection of a rectangle is then delta/2. And this is this term because we got 4 rectangular portions of the slab. Then for the triangles, we got 8 of them, 4 in each corner, and for one, it's B/3 times B/3 divided by 2, and the mean deflection of a triangle is delta/3. So then we got this expression for the work done by the external forces. You can work it out, and you find this simple relationship. We can now calculate the work done by the internal forces, and this is this yield line projected, so this axis of rotation, so it's m times B/3, and the angle of rotation is of course delta divided by B/3. And we got this 8 times. 2 times in each corner. This projected to this axis of rotation, or this projected to that axis of rotation. So we got it 8 times. E must be equal to D, and then we get the bending moment out of this, and which is 5 divided by 108 QB squared. Now we make a summary of it. We will know Q0 is the design load without reservation. It's given by this formula, and Q is the design load with the reservation, defined by this formula. For the same reinforcement of the slab, we can say that the two plastic bending moments are equal. So this will be equal to that. And from this equation, we will get the ratio Q over Q0. And we obtain this is 9 over 10. So it means that a loss of 10% in bearing capacity will occur when you make a reservation in the slab with a side B over 3.